I'm so happy you chose to join me for this little video clip where I'm going to be showing you how to do Lewis dot structures of ionic compounds. It's far more common to do Lewis dot structures for covalent compounds, but I still think it's a really helpful tool for our ionics as well. So these are the steps. You want to draw the Lewis dot structure for the positive ion. You may want to start with the atom. Magnesium has 2 valence electrons. Group 2 will always lose those 2 electrons. So now it has the same number of electrons as the previous noble gas. And if it's ionic, you have to show those brackets and your charges. So I like to think of IBC root beer, ions, brackets, charges. And then we want to do the Lewis dot structure for the negative ion. So chlorine has 7 valence electrons. It will gain 1 electron to have that stable octet that is the dream of every element except hydrogen, beryllium, boron. Okay, so that's a -1. Now, then when I teach how to do formula units, I always teach the lowest whole number ratio using the least common multiple. So both numbers divide into 2, and so I need 1 of those, and I need 2 of the chlorides, and so that gives me a +2, that gives me a -2, so I have a neutral formula unit. So I typically will put the one that I only need 1 of, or that I need the fewest of, in the center. So that's why I put the magnesium ion in the center, and then we can put chlorides on either side. Now, you'll need to talk to your instructor about how he or she likes this. My only goal here is that we alternate positive and negative charges, because negatives and negatives repel and positives repel. So I certainly would not want to put a chloride underneath another chloride. That would not work. But I could just as well have put that chloride underneath the magnesium. As long as you're alternating your positives and negatives, I usually give credit for this. Ion structures, the lattice is very, very complicated, and I don't even cover it in AP nor IB. Now, one more thing that I want to make note of here is this. I have a -1, I have a negative, positive attraction. That's called an electrostatic attraction. So your ionic bond is an electrostatic attraction. Now, if I wanted to, let me clear the screen a bit here. If I wanted to melt magnesium chloride, I would need to break that electrostatic attraction. So when you melt an ionic, you're actually breaking an ionic bond. That takes, remember, it takes to break. If you've watched any of my videos, I do freeze to form, takes to break. It takes energy to break a force of attraction. And so that energy that it takes to break would be very high. It takes a lot of energy to break those strong electrostatic attractions. So it would have a high melting point. A lot of energy to break, high melting point. Thought that might be worth noting when we had this little model in front of us. Okay, so now let's take a look at some examples that aren't completed yet. I'll likely do them quickly because I do know that you can rewind and you can slow me down, or as many of my students do, they tend to speed me up. So I have sodium, so I'm going to draw the sodium with its valence electrons. And then I have chloride, and chloride is in group 17, so it has 7 valence electrons. Okay, there is this fruit fly on my computer that's driving me nuts, you guys. Okay, so sodium, metals are losers, it wants to lose. And so I have a sodium with its plus charge. Chloride wants to gain that very electron. So if you look at it, this electron is going to be donated to chlorine to become chloride. So then I would have the chloride ion. Negative ion of is chloride. Make that bracket a little bigger. Now, least common multiple of 1 and 1 is 1. So I need one of these, I need one of those. So one's positive ion, one negative ion, and that's why the formula unit is written as NaCl. We've got to balance charges. Some teachers will talk about crisscrossing charges, and I caution against that. I've seen too many students make mistakes doing that. And it doesn't teach understanding, it just teaches a trick. And I like devices that help us learn and remember, but I don't like tricks that bypass understanding. Okay, so the calcium element, you may not need to do this. I'm going to go ahead and do this for clarity. Fluoride's group 17, so it has 7 valence electrons. And so the calcium ion will become calcium 2 plus. Fluoride only needs 1 electron to become F minus. So there's 2 ways you can think of this. One is that calcium is going to give 1 of its electrons to a fluorine to become fluoride. But that still leaves calcium with an extra electron to give away. So it will seek out a second fluorine molecule. The other way is that the least common multiple of 2 and 1 is 2. So I need 1 calcium and I need 2 fluorines. So I'm going to draw that second fluorine, which is now a fluoride, because it's the negative ion of on the side. So now I've got 2 negatives, 2 positives, and when I write calcium fluoride, I have a neutral formula unit. Okay, let's look at aluminum oxide. Aluminum has 3 valence electrons. It's going to lose all 3 valence electrons to become plus 3. So if you're in my class, you may have heard me talk about the silver stairs. So we have silver and then cadmium and zinc. And then we have indium, gallium, and aluminum. Oh, go away, little thing. Aluminum, okay? 1 at plus 1, 2 at plus 2, 3 at plus 3. Okay? Now oxide, oxygen has 6. So to become the oxide ion, it wants to gain 2 electrons. Okay? So now I want to make a neutral formula unit. The least common multiple of 2 and 3 is 6. So I'm going to need to draw 3 of my oxides, and I'm going to need to draw 2 of my aluminums. That would give me minus 6 and plus 6, which will give me a neutral formula unit. Okay, so I need this space. I wanted to show you that logic clearly. So I'm going to draw 1 of the oxides over on this side here, the right side. And all I personally care about is we alternate positive and negatives. So I can put an aluminum here, can put an aluminum here, or if I had room, I could do it on top. All I care is that I alternate my positives and my negatives. So there's my 2 aluminums. I've got 2 oxides, so I need 1 more oxide, and I could certainly sandwich it between. Again, I just don't want to put it right beside another negative charge. I could have put it down here or over here. Again, just alternate your charges. I had to draw 2 aluminums. I had to draw 3 oxides. So my formula unit is Al2O3. if I were to write aluminum oxide as a formula. So hopefully this is tying together some great information for you. And I'm so grateful you joined me. Thanks a lot.